Hi and welcome to what will be our last topic, acids and bases for high-level chemistry in this sequence. So we're going to be looking at Lewis acids and bases today, so let's get started. For HL Chem, what we're looking at in acids and bases is expanding our idea of Bronsted-Lowry into a different classification of acids and bases, which is Lewis acids and bases. Lewis acids are lone pair acceptors and Lewis bases are lone pair donators, which means that we're talking about nucleophiles and electrophiles that we saw back in organic chemistry. We also need to be able to understand the application of Lewis base theory to inorganic, so the transition metal complexes that we've just learnt about, and organic chemistry. The Lewis theory of acids and bases essentially allows us to consider compounds that aren't just aqueous. Remember from Bronsted and Lowry, we needed an aqueous system in order for proton transfer to occur. And not all the systems where we see acid and base behavior are actually aqueous. It also allows us to consider other molecules that don't contain an acidic proton but may result in a change of pH to the environment. This theory focuses on electron pairs rather than protons. With Lewis theory, acids are electron pair acceptors, which is in contrast to Bronsted-Lowry where they are proton donators, and bases are electron pairs donors rather than being hydrogen acceptors. Okay, so Lewis acids are electron pair acceptors, bases are electron pair donors. So this means that they don't have to have a hydrogen in their formula. Particularly Lewis acids don't need a proton because they're not going to have to donate it. What they are is electron deficient. They don't have a full outer shell of electrons. So they are very reactive towards any electron pair donor that may attack. Okay, so if we think about nucleophilic attack, they're going to be very susceptible to this. Examples of Lewis acids that we see are BF3, SO3, H plus itself, okay, because it will take on electrons, and then SbF5. They are electron deficient, so they're looking to gain electrons, so they are electrophiles. So Lewis acids are electrophiles. If we look at some more examples, there are a number of ones that we've seen now in our higher level studies of bonding, and these include metal ions when they are in water. So metal ions are acidic because they have that positive charge. They're going to draw electron pairs towards them, as we saw in the formation of transition metal complexes. Anything that is electron deficient, so positively charged, or in the case of BF3 has less than 8 electrons in its outer shell, is going to be able to act as a Lewis acid. The reaction between a Lewis acid will form a coordinate dative bond, okay, and this forms what we know as a Lewis acid-base complexes. These are the types of complexes that we've just come across in our study of higher level bonding. Okay, so you'll remember that we had transition metal complexes where we had a transition metal in the center, such as copper 2+, and then the ligands binding around that metal ion form a dative coordinate bond to that metal ion. So in our hydrated complexes, we would see that ligand bonding, which was a coordinate bond. That is a covalent bond because it is now sharing those electrons. Lewis bases, on the other hand, will have a non-bonding pair of electrons that they can donate. This means that things such as water, hydroxides, fluorides, the things that we saw forming good ligand groups, are Lewis bases. These will contain a lone pair of electrons that is able to be donated into the complex formation. So the non-bonding electrons are donated from the base to the acid, forming the new bond, as we see down here. In ammonia, we can see the formation of the ammonia BF3 complex, and again we see the lone pair from the ammonia bonding into the BF3 to form the new bond. This means because they are electron rich that Lewis bases are electrophiles. As we've been saying, the coordinate bonds between the ligands and central transition metal ions in transition metal complexes are examples of Lewis acids and bases. The coordinate bonds with the 6 water ligands on the iron complex here in iron 3 hexahydrate are a result of Lewis acid and base interactions. If we think that Lewis acids are the electron pair acceptor, we can see that our metal ion is the Lewis acid. And the water ligands, the ligands are taking on the role of the Lewis base. They are the ones forming that dative coordinate bond in the complex. So now that we have the 2 theories of acids and bases, you need to be able to classify them as either Bronsted-Lowry or Lewis acids and bases. In the case of Bronsted-Lowry, you need to be looking for the presence of that hydrogen in the case of an acid that can be donated, or whether or not they have a lone pair that could accept the hydrogen or that empty space in order to act as a base. It is all about proton transfer, though, for Bronsted-Lowry. In the case of Lewis acids and bases, you need to consider whether or not they have a lone pair of electrons, remembering that the acid will accept the lone pair, and the base is going to be the one donating the lone pair. All Bronsted-Lowry acids are also Lewis acids. Okay, so but not vice versa. Not all Lewis acids are Bronsted-Lowry acids. All Bronsted-Lowry bases are also Lewis bases. So the Lewis acid-base system allows us to classify including Bronsted-Lowry, but not all Lewis acids and bases would act as Bronsted-Lowry acids and bases. And that's Lewis acids and bases. I'll see you in class.